We are at the top of the hour, so it's time to begin. Today we're going to have a presentation by Andrew Lotto, who is a hurricane specialist at the National Hurricane Center, and he's going to be giving us an overview of tropical cyclone intensity guidance models used by NHC. So go ahead, Andy.
Hi, everybody. Thanks for having me. So I'm going to be talking about one of the biggest forecast challenges we have at the Hurricane Center, which is forecasting intensity for tropical cyclones. I want to go over with the different intensity models we look at here at the Hurricane Center, some of the strengths and weaknesses those models have. We want you to understand how these intensity models are used in what the forecast that we do make. Go over briefly some of the future model improvements of these forecast models, and I want you to understand the limitations of these forecasting, because a lot of these models have a difficult time resolving tropical cyclone structure, and it's still a very big challenge for us to try to understand rapid intensification and how that the evolution of the structure of the cyclone plays a big role in that. So how is it measured? First off, it's the maximum sustained wind. A lot of folks on the line probably know the definition of that. It's over 1 minute at 10-meter wind. Over the ocean, there's very few direct observations to actually measure 1 minute winds at 10 meters. And so there's other methods that we use for getting this information. Satellite imagery, the Dvorak technique provides an estimate of intensity. Reconnaissance is one of the closest methods we get to that 1 minute, 10-meter wind, where they can do drop stons. They can also do SFMR, which is a sensor on board the aircraft to try to measure. The drop stons, of course, have their limitations because they can only do them so often. SFMR, although it provides a higher resolution of the winds, it has its own limitations, and we're still trying to learn what those limitations are now. So we've seen some issues with shoaling, or in stronger storms, sometimes the winds appear they might be a little bit too high, and they work better when the storm's intense enough. So there's only a window where we can use them usefully. Then there's scatterometer winds. Those are 10-meter equivalent, but they're more instantaneous and they're at a lower resolution than what you expect for, say, a buoy taking a direct observation. So there's some data out there, but we have to make some adjustments based on the data that we see. So there's, if any of you were on the call last week, there's a similar spectrum of models that we use for intensity that we do for track. We have statistical models. These were specifically designed for the ship models and the LGM models. The statistical dynamical models are specifically designed for intensity. The ones above, the DK ship 4, the trajectory clipper, they do a little bit of both. Dynamical models, all familiar with those: HWRF, GFS, UK Met, GFDL, GFDN. The European model, those all have their own set of governing equations. They have a little bit of handling of different parameterizations and how they try to evolve things over time, so you always get a little bit of a different solution between them. Then you have the ensembles and consensus models, which is simply the ensembles are different members of the European, GFS, Canadian models, and then you have consensus models, which is a blend of compilations of the different models into one model. So the statistical intensity models, it's basically on climatology and persistence, so it has low skill. It's developed back in 1979. It's basically our baseline for the intensity. And so we base everything. If we're lower than that, we have no skill. If we're doing better than that, we have skill. So it's just essentially a baseline for intensity. Ship's guidance is something we use very frequently at the Hurricane Center. Essentially, it takes the different predictors, list of different criteria that can build into what affects intensity, and subtracts and adds to the potential intensity. And so it takes that information. The street surface temperatures ultimately comes from Reynolds weekly fields. The predictors are from satellite data, and so and I'll show you the example here in a minute. It's very useful in trying to determine what factors are playing a role into what could make this storm stronger or weaker. And here's the list of all the predictors that are in that list. And so there's a whole bunch of information here. And basically what it shows is like the velocity, maximum potential intensity is going to be based on these features down basically below number 7 and downward. And so all these ingredients can go into it to try to determine, right? So wind shear comes into play, the temperatures aloft, are they warmer or colder than normal, the ocean heat content, the moisture moisture between 700 and 500. These are all very important what plays into intensity. And so we come up with these numbers to try to determine what the storm's going to be doing over the next several days. So the factors that go into this, we call it DK shifts model. So it's one factor that subtracts the intensity when something's over land. So that helps us determine when it's over land for a certain amount of time, how weak the storm will get. And so this shows you kind of how it's subtracted over time. The limitation of the shifts model is that, well, if you add a bunch of different negative numbers together, you can get a negative number. So you can potentially say that intensity can go negative in extreme conditions. But these conditions are a little bit of a time lag, so it's not instantaneous. And so you might have a response to sea surface temperatures that's not as fast as it should be. And so you might have a little bit of high bias. Let's say if the storm's moving over 23 degrees Celsius waters in 24 hours, there might be a little lag. We saw that actually with Tropical Storm Christina that's now been written off. That shifts was showing where it's going to be 40 knots. It was about 30 knots. It just didn't spin it down fast enough. So that's one thing to keep in mind with the shifts model. LGIM is also listed on this intensity guidance, and I'll show you that here again in the slide in a second. It basically takes maximum potential intensity from a growth rate, and it plugs into the equation you see above. For those of you that are interested in the math, it comes up with the possible change in intensity over time. So the advantage of the LGIM, it doesn't go below 0, is for one thing. The time evolution of the predictors that we're talking about are accounted for more in real time, on the 6-hour intervals, and so that's more helpful. And the movement between water and land is handled better because of the time stepping, so it's not time lagging the decrease in intensity when it goes over land. Disadvantages, the model fitting is more involved, so it's a little bit more difficult to tweak, and inclusion of persistence is more difficult into the model, so it's a little bit more complex. The performance of the LGIM over shifts the last 10 years, this is the 2016 study that was done, shows early on in the East Pacific, the performance was actually worse, but over, basically what you're looking at is as we get farther out in time, the performance is better at LGIM in pretty much all time steps beyond 84 hours. So this is what it looks like when we look at the ship's guidance. So I know there's a lot of data on here. I want to just highlight the first 4 lines here. As we say, V no land, V land, and then V LGIM. So we're looking at ships, DK ships, and the LGIM, all these lines. So we start off at 50 knots in this column at 0 hours, and we go out from left to right through time to 120 hours. You can see the 3 different models in play here, and their values for intensity. So at 24 hours, you have the ship's models at 67 knots, and LGIM's at 70 knots. And you can try to determine what the factors are that are going into play. Well, why is the storm still intensifying here? Well, if you look at shear, this line down, the line just below that blank line there, shear shows 13, 13, 10, 10. That's only moderate shear. But then shear gets really strong later in the period, which helps to weaken the storm. So all these things, well, I won't list them all. You see, sea surface temperature, the relative humidity. You can look at all these values and infer what is causing this cyclone to possibly weaken or intensify. And it gives you a really good checklist to know what the environment's going to be like with this storm over the next several days. So I just want to say that the time lag, this is a ship's forecast because of the time lag, and building the parameters in to positive or negative can make it miss the peaks and valleys of the intensity. So it will tend to be a little bit more smooth but inaccurate especially during rapid intensification or rapid weakening. So we do have rapid intensification index. It's actually, if you were looking below in that worksheet, below what was on the screen is actually the RII information. we define it as any 30 knot or greater intensity increase in 24 hours. And so there's training built into the model to convert the information so that they can try to determine if all those parameters that are in that list are conducive or not for rapid intensification. And so it's looking at particularly these values. So the max wind change in the last 12 hours, is there momentum going on? Is there already increasing quickly? That's a player. Ocean heat content, shear magnitude, divergence of law, RH, the current change in the wind, and are the IR pixels colder than 30 degrees Celsius currently, negative 30. So that's also a player if there's a lot of deep convection that could possibly rapidly intensify soon if all these other factors are coming into play. Unfortunately, it doesn't always mean it's going to happen. Here's a good example of what RI might look like in our forecast. So we went from 75 knots currently to a forecast of 105 knots in 24 hours for Hurricane Rick back in 2009. This good example is Patricia. Patricia went from 70 knots to 135 knots. I'm sorry, this is actually still Rick. I'm giving you a little preview. We're going to show Patricia here in a minute as well. So here's what the RI guidance looks like. So it's a similar chart to what you were looking at before. And we can see it in the data here. This is ship's guidance again, the 70 and the 97. That's hinting that we could have a rapid intensification occurring. The numbers are getting fairly close. So there's this RI data down below, all these lists of numbers. And it breaks out these probabilistic values at the very bottom. So the probability of RI for 25 knots threshold is 78%. That's fairly high. 35%, 66%. So we have a better than 65% chance that the RI is going to occur. So that would give us higher confidence when making our forecast. Typically, if we're just looking at the numbers in the models and only a couple models show rapid intensification, and this index doesn't show it, we have fairly low confidence. We tend to not forecast rapid intensification in that case. But if we have several models and the RI index showing high confidence, we'll feel better about showing 35 knot wind increase over a 24-hour period. It's another example of what it looks like. It's similar to what the previous screen shows. It's just that there's a list that, if you look in the middle of the screen, shows ship's probability for rapid intensification of certain values over a certain amount of time. In this particular case, it's kind of mediocre. The values, the best I see is 24%. 25 knots in 24 hours. It's kind of hinting like that's the most likely intensity change you're going to see, whereas these other values are not as likely. And so you might consider the fact that it might see 25 knot increase in 24 hours more than these other specific incremental intensities. I was just hinting at this earlier. So Hurricane Patricia went from 40 knots to 185 knots in 48 hours. That's very rapid intensification, way beyond any of the statistical estimates for any of the probabilities we actually would ever look for. So this is a very extreme case of rapid intensification. So we talk about the dynamical models, the GFS, UK Met, and they are INCEPT, HWRF, and HMON. So these have the forecast errors that can go into these for intensity are due to the observation that go into it. So we have the sparse observations, the lack of data can really increase the errors over time. They're at inadequate resolution. So the HWRF, HMON are getting there. It can get better. We need the resolution to be as low as possible to resolve what's going on inside the storm better. The lower the better, because if we can resolve the mesoscale features going on inside, that will really help as far as rapid intensification forecasting. So some of these models lack this understanding, and they simulate the basic physics of intensity change, but they don't anticipate all the inner core things that are going on. Some of these models also have problems with representation of shear. If they're getting the large-scale flow wrong, they're going to get the intensity wrong over time. There's been improvements over the past few years of the resolution, physics, and data simulation, and they're going to keep happening as we move forward into the future. The limitations that we just talked about, the observations, the resolution, data simulation, we wish we had a way to really get through the core of these storms on a routine basis. If we are close to land, we have radar, and that's very helpful, but these storms are most of the time are not. close to land. It's hard to resolve these interactions with the boundary layer, radiation, microphysics. The ocean interactions are very difficult to resolve in these models, and it really does lower the predictability and intensity in a lot of cases. Models, properties, I'm not going to read all this off to you. We have links available so you can refer to this information later. We have a web page, hurricanes.gov/model summary. It's HTML that has really good insight to a lot of the model details. The HWRF model, if you're on last week, we say it's basically 3 grids. Outermost grid is very large. A middle grid is about 18 degrees by 18, and their innermost is just storm around the storm itself. And so you have these moving grids inside the outermost grid to try to forecast the movement and intensity of the tropical cyclone. And this also lists the different convective schemes, the ocean coupling, and how it's initialized. This is what the HWRF would look like when it's running. So you see the top left corner is the moving nested grid in the large grid. The storm is trying to simulate the storm's convection, which is very helpful in trying to determine its intensity. So you get those physical processes, what's going on inside the storm. Again, it still needs a little bit higher resolution to better perform with that, but we're making progress. HWRF upgrades, they're going to try to do 3 hourly instead of 6 hourly. The high resolution CMAP, that'll help with air-sea land interactions. The RTOPS data is going to be switched to RTOPS to initialize ocean for the basin. Same with the EastPack, that'll help out with that. And they'll update the trackers and improve the initialization of the vortex, which would be very important because if you don't have the correct vortex initially, you're not going to have a correct forecast anytime thereafter. And other bug fixes and et cetera that are going to be going on here next year or so. H1 is a very similar model, has a little bit of different ways of doing the ocean coupling. The gridding is a little bit different in size. So a lot of times you look at the forecast, the H1 and HWRF, you'll see, and I remember this with Irma and even with Dorian, the storms look very similar. And so there's a lot of similarities to these models. They just have some minor differences in how they resolve things. And the nested grid is always a little bit different than the HWRF. H1 domains are slightly different in size and structure. H1 is going to be increased, vertical resolution is going to increase this year. Dynamic core is going to be upgraded. Other physical enhancements are going to be made, initialization improvements, and again, other post-processing enhancements are going to be done as well. So here's the list side by side. If you're curious what the difference is between the two, not much. But there's just enough to make it so that these models will give a little bit of a different representation of the tropical cyclone. So it's good to have 2 to look at in a lot of these cases. So this is all the data that's going into the models that we're looking at. I'm not going to list them all here, but you have a whole lot of different radiances from the different microwaves and gyrometer data and geostationary satellites that are going into the models. You have the atmospheric winds going into the models. We have aircraft data that goes into models, and there's been a study that actually shows that the track error can be decreased by 25% by using the aircraft data, so it is very helpful. As an example, what it looks like when they're doing a bunch of drop zones around the storm. This Gulf Stream 4 example back with Hurricane Irene. So the data in the simulations of HWRF is going to be an idea how much has evolved over the last several years. We started off with just a couple of different pieces of information going into the HWRF. Now we have this entire list going into 2020. And so the data is exponentially gotten better for the HWRF. So we're hoping that's going to result in better intensity forecasting. Consensus and ensemble forecasts are very useful for us at the Hurricane Center because we're taking in the averaging different intensities from the different models. And so we have different intensity consensuses we can look at, which is good because there might be a model that's performing poorly and dragging down the consensus performance. And so we might switch to a different consensus. So we have the ICON, which has certain models built in, IVCN, which has certain models built in. And then you have the FSU Super Ensemble, which also has a different consensus. So and that's what's cool about the Florida State Ensemble. It learns from the past performances, and it trains it, and it counts for those biases. So these corrected consensus approaches, like at the Florida State Super Ensemble and HICA, the HPIP, it's very useful because we don't have to sit there and look at a consensus model and be like, well, has it been performing well? These models have been performing well lately. The models are doing it for us. It's very neat to have that kind of ability to look at a model that does that. So here's an example of how they perform. So for Hurricane Ike, which the hurricane symbol is what verified. If you look at ICON, the very light blue line, was really good at forecasting. That's a really good consensus blend. The H-work was over forecasting intensification, and the chips were too low. And so when you build out these biases and you blend them together, you get an accurate forecast. So we do model verification for intensity based on, well, we're talking about the Shift-4 model, the climatology persistence, and we subtract it from what the model error would have been from that to determine what our skill would have been. Sorry, I want to go back. It's important to know we don't verify extratropical stages. It's the time that the system's a tropical cyclone. If you're curious about what late versus early means, early models are essentially the ones that are available right when I run the guidance. So if it's 0Z and I submit my guidance, I get the early model data available almost immediately. And that's basically the shifts model. Shifts model is available to me almost immediately. For track, you see tab M, tab D, Clipper. Those are available just a few minutes after I submit it. The data we use when we do our forecast for, like, let's say our package that's due at 3Z, it's actually the previous model. So if it has an 18Z model, it's interpolated forward. So it's not instantaneous. It's time delayed, but it's still very useful in having that information because, obviously the models take a few hours to run. So when I send the model data at 0Z, it's not ready until the next run. And so basically most of the models we have that are very useful to us other than shifts guidance is the late models. So the early models that we're talking about, so we have the LGIM. So these are interpolated models. HWRF, LGIM's so instantaneous, D-shift is instantaneous. The other ones are going to be interpolated from the previous 6 hours. But looking at this information, our official forecast, thankfully, is up there towards the top, has some of the best skill. The IBCN and HICA, that's corrected consensus. So the consensus models are up there with our forecast. In the East Pacific Basin, we're not the best, the official forecast, but we're right up there with some of the best ones. So we're not too far off, only a few percentage points difference from the IBCN and Florida State Super Ensemble. So over time, the intensity error trends overall, if you take the smoothing of it, have been getting better over the course of years, especially if you look at the longer term ones. 120 hours has dropped by nearly, I'd say roughly about several knots in the last 10, 15 years or so. We can associate a lot of these improvements with model improvements. We have the H-work, the HMON, and then these corrected consensus models and the other consensus coming into play during this time frame has really contributed to a lot of these improvements. So other parameters we use in our forecast, if you were on last week, we talked about track. The Genesis is which are tropical weather outlooks we do, formation within the next 5 days. In 2 days, we have 2-day probabilities and 5-day probabilities. The radius of winds, so the wind speed radius, we tropical storm force winds, hurricane force winds at 50-knot winds, how far they extend out from the center of the storm. That's a big player in where we determine how big the warnings are going to be, the watches are going to be. It's also a big player in storm surge, which we forecast at the Hurricane Center. Larger radius, storm radius maximum winds, the larger those storm surge is going to typically be. The rainfall, we get that data from the Weather Prediction Center, and we put that into our key messages of what the impacts would be from that. We also put in our key messages the tornado impacts. We get that from the Storm Prediction Center. And from right next door in Taft B and also up in College Park, we get the 12-foot seas. Depending on where the cyclone is, we get the 12-foot seas from either in the tropics or up north in the Ocean Prediction Center. And all that goes into building our forecast and getting the word out to everybody of what the impacts are going to be, going beyond intensity and beyond the track. Because as many of us know, sometimes it doesn't take a Cat 5 to cause a lot of damage. Sometimes it can just be a Cat 1 or even a tropical storm causing torrential rainfall or a lot of tornadoes or a lot of surge from even those weaker systems. So to conclude, basically, the intensity forecasts are less skillful than track. We're a little behind on the intensity forecasts because these storms have so many different processes going on that affect how intensity changes. And as long as we are picking up on those internal physical processes, we're going to be not as skillful as intensity forecasters as we will be as track forecasters. And so it's a work in progress. The intensity techniques are still competitive with dynamical models. Saying that the SHIPS model is very good because it shows us visually and empirically how all these different parameters are coming together. The consensus approach is very good. It's been installed in the stats. It's some of the best performing models, so those are showing good promise and giving us confidence in our forecast. Wind structure prediction, that's also an important note to have as far as like the wind radii and how strong the winds might be closer to the core. So is it a larger spread out storm or is it very compact? It's important, but it's even harder to predict than intensity. So that's a very big challenge is doing the wind radii forecasting. And there's a lot of efforts underway down here in Florida and with our collaborators to try to improve the H1 and HWRF to make them even better. And we listed all those things before, and hopefully those will help things verify a little bit better going into the future. Here's a list of all the links to all these different model data if you're interested in getting that information in a little bit more detail. And at this point, I'm going to hand it back off to Imagery and Dan for any questions you all might have.
Okay, thanks, Andy. Hey, Dan, are we going to be able to unmute the lines? Or?
Yeah, we should be good. Let's just ask if anybody has any questions for Andy.
Well, I have one, if that's okay. Andy, what's your take on how good are the regional models nowadays at predicting RI, particularly H1, since that's relatively new?
It's storm dependent. I have to say, there's certain times where they'll hone in on RI when it shouldn't be occurring, and we're not sure if it's because of maybe they're not picking up on the shear as well. The external, the environmental stuff. And so it's taking the inner core of the storm and spinning it up very well. It's saying, okay, this storm can have high intensity, can have great radar signatures, but it might be neglecting as much as the shear and other negative environmental factors that were going into it. But so sometimes those environmental predictors, they're getting it right. And so sometimes we'll see it as the best performing one because the global models won't be able to pick up on the internal interactions as well. And so it's under the right circumstances, it can be better than all the other models, and under other circumstances, it can be worse than all the other models. And I think it does have something to do with the global models cannot resolve the inner core of these storms, and so when the global models have the environment right, and the regional models do not, the global models are going to be better. That makes sense.
Yeah, it does. So you kind of have to take it case by case.
you kind of have to know as a forecaster what the environment is based on what the global models are telling you and saying, well, this CH or for HMON, they're not seeing it. And therefore, you have to kind of discount it. But there's other times where you know the environment is going to be good and they're picking up on it, and then you have to ask yourself, like, well, they said to be 120 knots and it's in 48 hours it's 80 knots now. Well, they might be right, so they might convince you to nudge your forecast up a bit if you know the environment in agreement with it.
Makes sense. Are there any other questions? Okay, I think we can just wrap it up then. So thanks so much, Andy. We really, really appreciate you updating these. It has been a few years.